Hello and welcome to the sixth unit of AP Statistics, which is Inference about Means. The topics covered in this unit are hypothesis testing of means and confidence interval of means. If you watch my previous video about Unit 5, which was Inference about proportions, you will see that a lot of this unit will repeat itself. The difference between the previous unit and this is that this time we're dealing with means rather than proportions. However, a lot of the vocabulary as well as the construction of confidence interval and hypothesis testing will be awfully similar. If ever during this video you feel like I'm being redundant and you've already heard of what I've said before, feel free to skip along, and I will try to place annotations within the video so you can skip along to certain parts of the unit. Now, beginning with the vocabulary, we're going to talk about something called degrees of freedom, which in this unit will just be your number of trials minus 1. There's no standard definition for it, but this would be a good thing to remember. The standard error is again the standard deviation of the mean, and the margin of error is just the extent of error on either side of the interval. Now we'll look at confidence intervals. Confidence interval for one mean, or confidence intervals in general, are used to test if the mean is significant enough. In the previous unit, I talked about standard error. In this unit, we will also talk about standard error, but this time it has this first symbol divided by the square root of n, where n is the number of trials. Now, what is this symbol? The symbol is actually a lowercase sigma, which actually refers to deviation of the sample. Standard deviation. I know maybe in your other math classes you've heard of sigma as the summation, but this is a lowercase sigma. Now, for confidence interval, we use again the same thing, estimate plus or minus margin of error. But this time we use this. It's y bar plus or minus t star with n minus 1 degrees of freedom times SE, which is from here. Now again, it is t star, which is found from the standard model corresponding to the specific confidence level with n minus 1 degrees of freedom. Now in this unit, because a lot of it is redundant from the previous, I've put these places of gaps, the underlined area. It's for you to fill out to make sure that you still understand the concept from the previous unit. So maybe you can pause the video and try this section out for yourself. You've got these. A small margin of error relates to a more precise interval, whereas a large margin of error relates to a less precise interval. Now, what does that mean? It just means that, for example, if you have a small margin of error, it means your t star over here is fairly small. T star is fairly small means your confidence level is also fairly small, which just means that you're not that confident. But despite not being that confident, you're still pretty precise. Same goes if you have a large margin of error, your T star is pretty high. That means you have a high confidence level, but you might be less precise. It just means that you have a wider, when I refer to large margin or small margin of error, I just mean this has a larger spread. So for example, a small margin of error, let's say I said 60% confident, my margin of error could be something like this. And let's say my true mean is 0.45. But a large margin of error with a 99% confidence could be something like 0.1 to 0.9, for example. As you can see, both of these will capture the true mean, which is 0.45, but this is just a broader or wide range. Then, as you know, Z star in the previous unit, this is now T star. T star, Y bar, and mu. Mu and Y bar are just ways of representing the mean. Y bar is your observed value, mu is your observed value, whereas Y bar is your sample mean. Similar to last unit when we talked about Z star, if I wanted a 95% confidence interval, this would be the syntax. Inverse T, which you would actually have to type into your calculator, area under, comma, your degrees of freedom, which is n minus 1. So if I wanted a 95% confidence interval, it would be 0.95 times my degrees of freedom. Or you could count it as number of trials minus 1. That would also be acceptable. As this. With the two means similar to two proportion, we are saying we're using it to test whether both means are significant enough. Look at this, it does look awfully similar to the two proportion standard error. This time it's your sigma squared 1 over n1 plus sigma squared 2 over n2 all square rooted. This as well looks awfully similar. It is your sample 1 minus mean of the sample 2 times plus or minus t star times SE, which comes from here. Now again, I want you to try these conditions, see if you know them. These should actually say t interval. I will change that, but do try it for yourself for the t interval. Hopefully you managed to get these. If you couldn't, you could have gone back to the unit about proportions and copy it. So again, for one again, they should say mean. And sorry, there was a copy case error. Again, with one mean t interval, it's either your sample size is greater than 30 or approximately normal. It's an SRS, which we all know is a simple random sample. It's independent and it's less than 10%. Two means it is where the sum of the two sample sizes are greater than or equal to 40 or both approximately normal. Both SRFs, both independent of each other, and both sample sizes have to be less than 10%. A confidence interval, as I've repeated myself multiple times, it's very similar to proportions. First, you need to figure out what test it is. Figure out if it is one mean or two and state the test. It's important to know what you're using. So if they gave you one mean, you'd say I'm conducting a one mean confidence interval, or it's also considered to be a one mean t interval. Conducting confidence interval, so brackets and two mean t interval, etc. Check conditions, of course. Always check conditions unless stated otherwise. Does the question say that the conditions are met? Next, write down the formulas needed. Your general formula, which is y bar plus or minus t star times your standard error. Next, find confidence level. Generally, in most questions in the AP exam, they'll ask you in subsequent questions what the confidence level is, or they will ask you what your margin of error is, and this would be a good step. Next, you want to conduct a test. Very simple. If you're on a T-inspire, the controls are menu statistics confidence interval. Now you look at T interval or two sample T interval. And when they ask you for X bar, you input the mean, standard deviation into S of X, and number of trials into N, followed by a confidence level. If they ask for 95%, you put 0.95. Then you have to write your interval in the form lower bound, comma, upper bound, and conclude. For example, if your interval was 0.1, comma 0.5, write like this, and we are followed by a confidence level. So if it was 95, we would say we are 95% certain that the true mean of whatever variable you're looking at lies between 0.1, comma 0.5, which is, or you could just write between 0.1 and 0.5, our interval. And of course, as always, you draw a picture of your normal model. Now, a good way to do that would be like this. This is what I took from the previous unit. So, for example, if you had a 97% confidence interval that went from 0.325 to 0.425, this would be a good way to draw it. You can whip it up in a couple of seconds. You draw your curve, you draw dotted lines to indicate your interval, and maybe if you wanted to, you could even shade in this middle portion to show that, yes, that is my interval. If the value is outside your interval, we say it is statistically significant. So if you were in this interval and we had 0, since 0 is outside our interval, we would say 0 is statistically significant. Hypothesis testing. Again, there's no change from the hypothesis testing. It will still contain a null and an alternate hypothesis. The null being when the mean is no change from the traditional value, and alternate hypothesis when the mean is greater than, less than, not equal to the traditional value. If it is not equal to, so when your alternate hypothesis had this symbol, we would then call it a two-tailed test, and we must multiply the p-value by 2, otherwise it is a one-tailed. Now, a one-mean hypothesis test is used to test whether the given mean is significant enough. Again, standard error is your lowercase sigma divided by square root of n, or your sample standard deviation divided by the square root of n. Conducting the test, again, your null would be that mu is equal to some value. But this time, your mu doesn't have a boundary. It can range from anything to anything. It has your boundary as negative infinity to infinity. Generally, you won't have infinity. But unlike proportions where you had 0 to 1, this can be anything. If it's negative, positive, anything. Then you have over here your alternate, which would be a not equal to, greater than, or less than. Then similar to the last unit where you had z value, now you have t value, which is your y bar minus your mu over your standard error. Sample mean minus your observed value divided by your standard error. Then when you put it into your hypothesis test and you conduct it, you will get some p-value, and then based off what your test is, either multiply it by 2 or try to conclude. There's again no change in the standard error, and your hypothesis test would be something like this. So mu1 minus mu2 equals x, and then your alternate would be I don't know why this confidence interval. P-value is now your y1 or y bar 1 minus y bar 2 minus mu1 minus mu2. Generally, this mu1 minus mu2 part equals 0. So because you're assuming the null hypothesis to be true. So if this x value is equal to 0, you could do that. Your t value would now read like this. There. That would be a perfectly acceptable answer. But if the reason I keep it here is because sometimes when the mu1 minus mu2 is not equal to 0, you're going to have to find that value and put it in. Now again, your conditions, if you would like, you can fill this out. So pause the video and quickly do it. Otherwise, if you remember, it is the exact same as for one mean as well as for my z interval and z test. So I'm going to quickly fill that up. Either your data is approximately normal, or your single sample size is greater than or equal to 30, SRS, independent, less than 10% of the population, or for two mean both approximately normal, the sum of these sample sizes is greater than or equal to 40, both SRS, both independent of each other and independent, and both of them are less than 10% of the sample. Pair is very similar to one mean testing. It is used to test if the difference between the means is significant. Why I say the difference, and why is it matched pair? So matched pair means that these variables are matched based on some characteristic. Like due to height, we will match person A and person B together, person C and person D. One mean testing could be just testing if a mean is significant. Two mean testing would test if just the means of two populations are different. This is to test whether there is a difference between two variables of possibly the same population. And standard error is just s over square root of n. And this time your degrees of freedom are -1, where n is the number of pairs. Now for the previous testings, we have said that n is the number of trials or number of values. This time it's n where it is the number of matched pairs. So if you had, for example, 16 values and 8 pairs, your degrees of freedom would be 8 minus 1, not 16 minus 1. For a hypothesis test, you would have mu d. You'd have to write mu d, and you'd have to define what mu d was. So mu d is mu1 minus mu2, or whatever mu. Let's say you're looking at height of grade 12s and height of grade 10. So mu d is mean of height of grade 12s minus mean of height of grade 10s. And then accordingly you'd have this. And for your t, you would have your difference, which is this portion over here, which I refer to as x. You'd have x over all of this. So that's why mu d. Maybe I should make that more clear. I'll put that in there rather. Mu with the subscript. Confidence interval, you would just, wherever you saw for one mean, you had y bar, you would just switch that to mu d. Again, using the t-value, you can determine the probability of the given p-value is significant to the z-value for proportion. Using the t-value can help you determine the probability that the value given, which is the p-value, is significant or not. So it will return a specific p-value. Conducting a hypothesis test, as again in the previous unit, you first need to figure out if it is one mean, two mean, or matched pair, and state the test. Secondly, you need to check conditions unless stated otherwise. That is standard. Check conditions unless stated otherwise. Thirdly, you need to write down your formulas. So up to here will give you all your step marks. This is your additional one, which is find the t-value, because they do ask for follow-up questions. Conducting your test will give you most of your points. So if you're in TI Inspired, the controls are menu statistics 7. So the t-test, which would be your one mean or matched pair test, and two sample t-test would be your two mean t-test. So for mean, whatever mean you have, you didn't put it into mu0, so your mu of your value into mu0, the mean of your sample into x bar, your standard deviation into s of x, the number of trials into n, and your alternate hypothesis. For it generally wouldn't ask you for your degrees of freedom, so you just have to input the number of trials. And then finally for step 6, you have to conclude. So let's try it. You guys can test or try this yourself as to what would happen if your p-value is less than 5% and then the other one where it's greater than 5%. Pause and try it out for yourself. You got these two correct. So if your p-value is less than 5%, or whatever alpha level they give you, it's a low p-value, so you'd reject your null, and there's sufficient evidence that your alternate hypothesis, which is in bold, whatever you have to input, is correct. If your p-value is greater than 5%, it's a high p-value, you'd fail to reject the null, and there's insufficient evidence that the alternate is correct. In my previous video, I explained why you don't say the alternate is wrong, because just because there's sufficient evidence that it is not correct doesn't mean that it's wrong. There's a fine line between that when we do statistics. But generally this is how you'd write it. If I were to grade a question like this and you followed all 6 of your steps and there were no calculation errors, you would definitely get 100%. Now that you know how to create a hypothesis test and a confidence interval, let's see if you can figure out how to do it. Now you could pause and try this yourself, or you could just go along with me, because I'm going to copy the steps down and use them as a blank template. The question: is the increase in mean weight of men in the year 1990 to the year 2010 statistically significant? Assume conditions for inference are met. And this is what they gave us. So the mean of the weight in 1990 was 68 kilograms with a standard deviation or standard error of 3.2. And in 2010 was 74 with the standard error of 1.9. So now, given what they told us, we need to figure out what sort of test it is. Now, based on what they have, they said increase mean weight of men in the year 1990 to the year 2000. So we know that there are two means involved. So it's a two mean t-test. Check conditions. Well, it says assume conditions are met. So we're going to write that down word for word. Assumed conditions for inference are met. Now you have to say where you got it from. You can't just say the conditions are met. So we write given in the question. If I could, I would honestly draw a line from given in the question to where it states it in the question. Write down the formulas needed. Pause if you would like, or you can again follow me. So we need to look at our null, our alternate, and our t-value. So for null, we know that is there an increase in mean weight? So since it doesn't say what exactly it is, we would keep it as a 0. is there an increase? Now it all depends on how we write this. So if I said mu1 was equivalent, sorry, mu1 meant the, sorry, mu1 was the mean weight of men in 2010. I'm going to leave it like that. And for, sorry, that would actually be 2. For mu2, I would write mean weight of men in 1990. Of course, you can do it the other way around. It is perfectly acceptable. No worries. So now the question asking, is there an increase in mean weight of men in the year 1990 to the year 2010? This may seem a bit confusing, but it just asks, is there an increase from the year 2010 and 1990? So is 2010 greater than 1990? Based on how I made this, which one appeals to you to be the right answer? It's the last one, obviously. So is 2010, sorry, is 2010 greater than 1990? Boom, that's what it is. Now for t value, it's your y1 bar minus y2 bar minus your mu1 minus mu2. And now we know that since mu1 minus mu2 is 0, assuming the null to be true, boom, that's fine. And you know what your null, you know what y bar 1 and y bar 2 is. So since there are no follow-up questions, this could actually be omitted, but I'm going to do that. Find the t value. I'm not going to bother. Let the calculator do it. In stats, a lot of times you can let the calculator do it. Now conducting the test, I'm going to take a screenshot of what I inputted into my results and I'll post it onto this. Pause if you'd like to do it yourself. Do realize that in the question I never stated what the sample size is, so I just quickly added that in. In this case, just let the sample size of each be 100. So I went and did my my calculator controls, which was menu 6 stat test and then 2 sample t test. When it asked me for data or stats, generally, I know I forgot to mention this in the previous video, but unless you have a list, like an actual list of data, you click on stats because that's how you input this. So in the previous video as well, I did kind of the opposite of what I was supposed to do. I let the second part of my hypothesis test equal x1 and my p1, and that was confusing. So I let x1 equal my mean of 2010. So I put 74, then the standard deviation, then my sample size, and then my second one, which was sorry, I see I've made a mistake. It should have been 3.2 rather than 32. So I'm gonna make that edit and then come back quickly. Right, so this is back to the correct value, 74 with my mean, 1.9 of my standard deviation. I put a sample of 100, 68 mean, and so on. Then similarly on the second part of the remainder of the same page, and my alternate hypothesis, because I let u1 or mu1 equal to 2010, that should be greater than my 1990, and pool you always keep as no. We don't use that in AP statistics. Now this final outcome has a lot of junk, but I want you to focus on 4 key aspects: the alternate hypothesis, the t, the p-value, and the df, or degrees of freedom. So alternate hypothesis, I want you to make sure, because I want you to make sure that you are inputting the correct alternate hypothesis. Sometimes students will mix these up and you will get a value that just doesn't make sense. Your t is important because if they ask you in the next question what is the t value, you can show this. P value, because that's how you conclude. And degrees of freedom, when we were talking about one mean, we were discussing how degrees of freedom was n minus 1, and for match pair is number of pairs minus 1. But here you can see if we did that, you would have 99, but it's not. It's this weird number. You never have to calculate it on an AP exam for 2 means, but you have to figure out that once you calculate your t statistic and you do your test, you can now answer the question. Now we need to write out p-value and conclude. So first let's look at the p-value. 9.865532. That's my p-value. Nope, that is not correct. As you can see, this is e, which just means times 10 to the power of, followed by negative 36. So my p-value, if I write it down here, my p-value is 9.8655 times 10 to raise to the negative 36, Or if you wanted to, you could just write approximately 0. Now, given that it's a low p-value, it's below my 5%, so low p-value, very low p-value. Now we gotta fail or reject the null hypothesis, sufficient evidence that our alternate is correct. And what did our alternate state? Exactly, that the mean weight of men in 2010 was greater than the mean weight of men in 1999. Sufficient evidence that mean weight of men in 2010 is greater than mean weight of men in 1990. So that's how you answer that question. There are a lot of things going on. If you have to rewatch that again, it's perfectly okay. Question. A group of students wants to determine the average time taken to solve a chemistry test. They randomly take a group of 20 students from the entire student body of 250 students and place them in different rooms so that no two students' answer impact each other. After the test, they find that the mean time taken was 63.4 with a standard deviation of 1.73. Create a 99% confidence interval. So, information given, we need to figure out whether it's one bean or two, and we gotta state the test. Or it could be matched pairs. Or matched pair. So, a group of students want to determine the average time taken to solve a chemistry test. So, the average time. They randomly take a group of 20 students from an entire student body and place them in different rooms. Then no two students answer impact each other. After the test, they find that the mean time taken was 63.4 minutes, with a standard deviation of 1.73. Now that it doesn't say two populations, it doesn't say paired by anything, so we're gonna conclude that it's a one mean z interval. Now this is the part where most students forget. Check the conditions. Nowhere does it say that assumed conditions are met, so we're gonna have to check this by hand. So firstly, what was the first condition? That n is greater than 30, correct? That is not true here. As you can see, it's 20. However, in these situations, you would write not fulfilled because, or not, or for n greater than 30, failed as n equals 20. So in these situations, I would normally or the teachers would normally provide you with a graph to show that it's approximately normal. But anyway, you need to continue with your testing. The data makes no sense, but you will continue. Or, I'll just change this value to 40. So yes, as n equals 40. That just makes it easier. The next one is both s, or in this case, just SRS. Yes, stated in the question. Where does it say that in the question? They randomly. That's good enough for me. The next one, independence. Are they independent from one another? They place them in a different room so that no two students' answer impacts each other. I'm going to conclude yes, stated in the question again. Most of the times these are stated in the question. And if you can remember, the last one is that n is less than 10% of population. For this one, you have to show your calculation. So what is 10% of 250, which is equivalent to 25? N is greater than 25. Yes. 40 is greater than 25. Next, we have to write down the formulas needed for a confidence interval. So the formula is this formula over here, where degrees of freedom is n minus 1, which is equivalent to 39. You have to write this down. Now, confidence level, they said 99. So how I'm going to find this is t star is equivalent to inverse t of 0.99 comma 39. And if you do that on your calculator, it comes up to a value of 2.425841. I'm going to keep it at 2.426. That's good. Now we know our confidence level. Now we just need to conduct our test. We can do all of this. Let's just do that. I'll put again how you should do it on your calculator into the video. In my calculator, I went to menu statistics, which was 6. Then I went to confidence interval again, which was 6, followed by t interval. Then I went to stats, and then I inputted my values. So for mean, which was x bar, I put 63.4, which is what we gave here. S of x, which is 1.73, and my confidence interval 0.99, and my n of 48. Now eventually you get values like this. Again, a lot of it is junk. You see degrees of freedom is now n minus 1, your S of x, which is standard deviation, n, margin of error, mean, and now your interval. Now as you can see, step 6 is write your interval in the form lower bound, comma, upper bound, and conclude. So we are going to do exactly that. So let's take a look at what our interval is. 63.6593, which I rounded, comma 64.1407. So that is our interval, and we are 99%. So I'm going to put that 99% sure or certain or confident. So I'm going to write confident because I like that. That our true mean of what? The true mean of time taken to complete the chemistry test. So true mean of time taken to complete the chemistry test lies between these numbers, which are our interval. So lies between this, and I put a comma there, our interval. Now you have to draw a picture of the normal model, which again I'm going to insert here, so give me a second. For your drawings, this is sufficient enough. You have your confidence level in the center, your lower bound, your upper bound, and just the normal model. This should give you full points. Just put a comma in there so you know what I'm talking about. And that would be it. Thank you so much for watching this Unit 6 video. Again, this was fairly long. If you made it through without skipping, it's good. You probably learned more. Maybe some parts were redundant, but that is just due to the nature of this lesson.